Hi, welcome to my talk on disentangling safe and unsafe image corruptions with anisotropy and locality. Today we're going to talk about adversarial robustness. In adversarial robustness, to measure, we define a threat specification where D is a threat function and epsilon is a permissible threshold. A threat function measures the level of threat presented by each corruption. The set of maximum permissible threat. Tau robustness this way is defined for every classifier at every input as a label prediction being invariant to the local neighborhoods defined by the permissible set. Prior work often uses LP norms, which are isotropic and global, and in this work we propose a normal specification to measure robustness beyond LP norms. So let's first look at some of the failure scenarios of LP threat. We first categorize corruptions into two categories: safe corruptions that preserve the true label and unsafe corruptions that modify the true label. Ideally, the permissible set should include only safe corruptions and should exclude all unsafe corruptions. In this figure, delta 1 and delta 2 are two corruptions that are equidistant from the original input. For some scalar t, we extend the corruptions along these directions to obtain new corruptions t delta 1 and t delta 2. We can observe that delta 1, delta 2 and t delta 1 are safe while t delta 2 is unsafe, and this makes us ask the question, what is the actual optimal choice of a permissible threshold? Choosing the threshold to be epsilon excludes t delta 1, resulting in underspecification. But choosing it to be t epsilon includes the unsafe corruption of t delta 2 and leading to an overspecification. And this issue arises because L infinity norms are unable to separate safe and unsafe corruptions for any epsilon. We said that the ideal threat specification should include safe corruption and exclude unsafe corruptions. Looking at this figure, our insight is clear. To do this, we necessarily require a threat function that is anisotropic, i.e., it varies across the directions of perturbations. It's local, that is, it varies at each input, the shape of the neighborhoods vary, and task driven, it's specific to the decision boundaries of the ground truth classifier. In our work, we propose such a threat function. Let's assume for now that a true labeling function exists, h star. H star of x is the true label. At every input, we collect two quantities. One, the directions of unsafe corruptions. These are simply L2 norm, unit L2 norm, direction vectors that correspond to unsafe corruptions. And the distance to boundary G measures the maximum amount you can travel along each unit norm direction while still having the same label. With these two quantities, we define the exact notion of projected displacement threat. Our first takeaway from our definition of PD star threat is that it's anisotropic and local. It's anisotropic because at every input, the threat function depends on u of x, and the inner product depends on the perturbation. We show in our paper that there's a principal trade-off between robustness and correctness. In particular, H star is guaranteed to be one robust at all inputs, and for any classifier that is not one robust at an input necessarily has adversarial examples. This way, we have a principled threat specification. Although we have decided a specification with a known trade-off, to compute this in practice, we require access to H star, which is unknown. But we do have access to training data. And so we suggest a heuristic empirical approximation of the two quantities that are required to compute our threat function. For the directions of unsafe corruptions, we compute subset of the directions based on the training data. And similarly, the distance to boundary is approximated heuristically based on the training data. Together, this results in our empirical proposal, approximate projected displacement threat. As an example at a glance, we show many perturbations with their corruption types listed above and the corresponding PD threat. We observe that intuitively P that matches our notion of signal degradation, our intuitive notion of signal degradation. And specifically, malicious corruptions that actually change the label are ascertained to have a larger threat. This phenomena is not just a cherry-pick example, it also has borne out in on average statistics across the entire data set. And for more details on this, you can see our paper. Our key takeaways are that there is a novel, flexible, task-driven threat specification that is capable of separating safe and unsafe corruptions and local and convex permissible sets. Thank you.